Hello, my name is Lisbeth Tejera, and today we'll be talking about SLO4, which is compare and contrast the components, processes, and directionality of prokaryotic and eukaryotic replication. First, the outcome of replication is semi-conservative, meaning that every daughter duplex contains one parental strand and one newly synthesized strand. It explains why mutations can be traced to specific template strands in lineage experiments. Replication initiates at origins and proceeds with two forks moving bidirectionally. This doubles the number of active replisomes and shortens S phase, whether you're at a single bacterial origin or thousands of eukaryotic origins. The chemistry is the key consistent. DNA polymerase can only add nucleotides at a free 3' OH, so synthesizes from 5' to 3'. To do that accurately, the enzyme must read the template from 3' to 5'. When a mismatch sleeps in, a replicated polymerase uses the 3' to 5' exonuclease to back up one base, exercise the error, and resume its synthesis. This is proofreading, and is a major contributor to correctness. Because polymerases are 5' to 3' only, each fork is asymmetrical. The leading strand is synthesized continuously in the same direction as the fork movement, and the lagging strand is synthesized discontinuously as Ozagmi fragments, each starting from a 3' OH and later stitched together after primer removal and ligation. In bacteria, these fragments were roughly around 1,000 nucleotides, and eukaryotics are shorter, due to part of the nucleosome spacing. So the big picture, bidirectional forks, 5' to 3' synthesis with 3' to 5' proofreading, and continuous leading and discontinuous lagging strands. Let's contrast how replication kicks off and is controlled in prokaryotics versus eukaryotics. In prokaryotics, the genome is singular circular and chromosomes with one origin C. DNA A recognizes DNA boxes at origin C and mounts the AT-rich region. DNA A then loads the helicase DNA B via DNA C. And as fork starts to move, DNA gyrase, which is topoisomerase 2, release positive supercoils ahead of the fork, so the ribosome can keep processing. Replication continues bidirectionally until forks meet or are blocked by the TUS-TER sites, which function like a one-way gate to communicate termination. In eukaryotics, replication starts at multiple points of the origin across the genome. Each new segment begins with an RNA-DNA primer. The core machinery includes inhibitory protein, a helicase to unwind DNA, and a topoisomerase to manage the torsal strain, and DNA ligase to seal the nicks. Remember, DNA is synthesized from 5' to 3', while the template is read from 3' to 5'. Unlike bacteria, eukaryotics uses separate DNA polymerase for the leading and lagging strand, and the ribolome is using a sliding clamp and sliding loader to maintain progressivity. On the lagging strand, FEN1 and RNase H removes the primer, and DNA polymerase fills the gap before ligation, because synthesis is discontinued. Remember, Okazaki fragments are about 200 nucleotides in the eukaryotic. Okay, now we're going to do an overview of the differences and similarities of prokaryotics and eukaryotics. Prokaryotics, remember, they have a single point of origin of replication. They use RNA primer. They have initial proteins, helicase, topoisomerase, and DNA ligase. Like the eukaryotics, they synthesize DNA from 5' to 3', and they read from 3' to 5'. They use one DNA polymerase for the leading and the lagging strand, and have sliding clamp and sliding loader. They have exonuclease of DNA poly 1, which removes the primer, and DNA poly 1 fills the gap. And RNase H backup for primer removal. Remember that the Ozagmi fragments, which are in the lagging strand, there are around 1,000 nucleotides in prokaryotics. Now for eukaryotics, there's multiple points of origin of replication. They have RNA-DNA primer, has initiator protein, helicase, topoisomerase, and DNA ligase. They use separate DNA polymerase for leading and lagging strand. They also have a sliding clamp and sliding loader. They uses FNN1 and RNA-H to remove the primer, and DNA poly fills the gap. Remember, in the lagging strand, the Ozagmi fragments are around 200. Now we'll be moving into our NBME style question. A mutation in a human cell disrupts the assembly of the clamp loader at replication forks. DNA synthase initiates normally, but both leading and lagging strand polymerase show frequent dissociation. Which component loss best explains these findings? A. Initiator proteins. B. Helicase. C. Sliding clamp. Or D. Topoisomerase. I'm going to give you a couple of seconds for you to answer. If you said C, sliding clamp, you are correct. Thank you so much for listening and have a great day.